The Physics of Track and Field by Joey Missan and Ben Cluver. Let's start with some background. According to some literature, the only event at the first 13 Olympic Games was the 600-foot foot race. After 776 BC, the Games were held every 4 years and had 3 foot races, the Stadion, Diablos, and the Dolichos. There was also the pentathlon, which consisted of discus, javelin, long jump, wrestling, and foot race. The first NCAA championship was held in 1921 for men's track and field. Women were allowed to compete in Olympic track later in 1928. Now onto the physics of the sport. Pole vault is an event where the athlete attempts to get as much vertical height as possible by building up speed, then transferring energy through a pole to get over a bar. At this moment, the kinetic energy is at its max and the potential energy is at 0 since the height is 0. Here, the potential energy is at its greatest and the kinetic energy is at 0. To find the maximum height a person can jump, we first use the kinetic energy equaling the potential energy equation.
We then rewrote the equation to find the maximum change in height for a pole vaulter going at their standard velocity while attempting a pole vault. For this, we used V is equals displacement over time. For this, it found 28 meters over 3.23 seconds for Colin equals 8.67 meters per second. To find the height of Colin's navel, we took his height in inches, which is 69, and multiplied it by 57% to get his navel height in inches, which is 39.33 inches. Then we took the navel height in inches and multiplied it by 0.0277 to get his navel height in meters. We then found his maximum height by taking 1/2 times velocity squared over the effects of gravity, which is 9.80 meters per second squared, plus the navel height of 1.09 meters to get the final answer of 4.91 meters as his maximum height. To find the maximum height of Renaud, we then used the same equations as for Colin. For Renaud, this was a distance of 40 meters over 4 seconds. To get a velocity of 10 meters per second, plug into the equation of 1/2 10 squared over 9.80 plus 1.09 meters equals 6.19 meters as his maximum height, which is very similar to his world record of 6.16 meters. We then created an Andrews chart for shot put projectile. We knew the acceleration, distance, and times. We knew that the times were 1.08 seconds by watching the video, and we knew the distance was 7.62 by measuring how far the ball went after the initial launch. To solve for initial velocity horizontally, we used the equation d equals VIT plus 1/2 AT squared. Then, because acceleration equals 0, the second half of the equation can be ignored, so you end up with 7.62 meters equals VI times 1.08 seconds. We then plugged vertical displacement and vertical acceleration in to get a vertical velocity of 3.35 meters per second. Then to find final velocity, we took initial velocity plus acceleration due to gravity times time to get a final velocity of negative 7.24 meters per second. We then completed another Andrews chart where the accelerations are the same, however time is 3.1 seconds and horizontal distance is 23.12 meters. To find horizontal velocity, we use the same equation as for the amateur. We use 23.12 equals VIH times 3.1 plus 1/2 0 times 3.1 squared. Since acceleration is 0, the second half can be ignored to get an answer of VIH equals 7.45 meters per second. The vertical displacement was found by using the launch height of someone who is similar in height to the professional. We use the same equations as before to get the equation negative 2.24 equals VI times 3.1 plus 1/2 negative 9.80 times 3.1 squared to get an initial velocity of 14.5 meters per second. We use the same equation as before to find final velocity vertical. We took the initial velocity plus negative 9.80 times the time 3.1 seconds to get final velocity of negative 15.9 meters per second. We then added in the units to complete the Andrews chart. We then found the height of Nathan in inches, then multiplied to find his height in centimeters. We then took half of his height in centimeters to find his radius, which is equal to half a wingspan. And we used the equation mv squared over r, which to find centripetal force. V equals circumference over time. Circumference is 2 pi 0.89 meters over 0.96 seconds, which was found from the video. Velocity equals 5.82 meters per second.
We then plugged in the velocity into the centripetal force equation using the mass of the discus and the radius of the wingspan to find total centripetal force of 60.9 newtons.
We then did the same thing for Jurgen, finding his height in centimeters and then dividing by 2 to find his radius as in half his wingspan. We found his velocity to be 2 pi 0.97 meters over 0.75, his velocity of 8.08 meters per second.
We then plugged in Jurgen's velocity in with the centripetal force equation along with the mass of the discus and the radius of his wingspan to find the total centripetal force of 134.6 newtons.
On your marks. Get set. Go!
For this block start, we created a free body diagram to model a situation. There was weight down, normal opposite weight, friction going back, and push from the leg perpendicular to the block. We also found that the weight equals normal plus friction, and the push is greater than the weight and the friction combined. We then used the formula for kinetic energy 1/2 times 93.89 kilograms times 10.44 meters per second squared equals 5,116.7 joules, which gives you the total kinetic energy from the race. We then wanted to find Usain Bolt's acceleration throughout different portions of the race. We used the hurdle marks on the ground to determine the distance used for each portion of the race. We then took the distance and divided it by the time, and then divided by the time again to get the acceleration for this period of time. We repeated this process to find the acceleration of 1/4, 1/3, 1/2, 2/3, 3/4, and for the entire race. As you can see, the average acceleration decreases as the race length increases. This is because, as the race continues, the runner is more focused on maintaining their velocity rather than accelerating more.